my initial angle was a -30, and then we put 20 milligrams, 40 milligrams, 50 milligrams, 70 milligrams, and then 90 milligrams. And these are the twist angles that we needed to restore the balance, the torsion balance. And so that is that. And let's go ahead and find our spring constant, okay? Without further ado, I am going to select on B, and what I want to do is insert, all right? So take this time to bring up Microsoft Excel, okay? Follow what I'm doing. Learn how to use Microsoft Excel, okay? So I'm going to go ahead and enter. And now we want to convert our mass from milligrams to kilograms. So I'm just going to select this field handle. It's this little dot in the lower right-hand corner. I'm going to drag to the right so that I don't have to really type that again. And instead of having milligrams, I know that I'm going towards kilograms. So what I want to do is I want to convert what I have here. I want to convert from milligrams, and I want to convert that into kilograms, okay? So once I have it set for 1, okay, I want to just go ahead and pull this down. And you'll see that all of these conversions have taken place. If I were you, I would test it. I would do the mathematical stuff on my paper. I would go hardcore for at least one of them. Make sure that one of them is correct, because once you have one correct, you could just apply it to all the other ones. This is the power that I am granting you. It's great power comes great responsibility. Okay, so we have our mass, and we have our mass in kilograms. What I'm going to do here is I'm going to go ahead and insert, because we want to find the gravitational force acting on the sphere to be charged. So gravitational force acting on the sphere to be charged. And that's going to be in newtons. All right, so that looks big and weird. So I'm going to go between C and D. I want to click. I guess this is left click. And I'm just going to open this up so that it will look readable. All right. And then I go, so if I pull this down again, so you see how it's big. If I go between 1 and 2 and then double click, it'll make it smaller. Okay. So just so it wouldn't take up, so it won't take as much real estate. All right. So let's go ahead and say equals to, we know how to calculate the gravitational force, because we know if we have a mass, we just multiply this by, oh, they don't have gravity in here. I was being a little excited. And I'm just going to double click, and you'll see that we have our calculations for the gravitational force. It's like 10 times 2. Okay. And so I don't know why this is 2. Should I give it more decimal places? Okay, so let me do that again. Just going to drag this down. So we typically would just have 2 decimal places because of our mass. So our mass has 2 significant figures here. All right. We probably can get away with at least like saying 20.0. We probably can get away with that. So any 2 ways, we can have 3 significant digits here. Let me go ahead and make these 3. All right, because I actually want to see those things. All right, so now let's use a function called the Linus function. So I'm just going to do function here. All right, and I'll put what the function is actually going to look like. So I'm going to say Linus, select that. So I need to know my known y's. Remember, we're looking at the ratio or the slope. Let me just say the slope of the gravitational force to the wire twist angle. Okay. So here, I just want to be as descriptive as possible because I am going to forget everything on purpose. linest. So we have our known y's here, all right, comma, and then we have our known x's. You see right down here, it's asking for those things. So what's going to be on the horizontal axis, what's going to be on the vertical axis, and then we need a constant. So it says false. If you put false in there, it's going to set the y-intercept to 0. So I'm just going to put in false. And then if I set false again, it's not going to return any additional regression statistics. Now, that's going to be useful when we need the standard error. So this is going to be the slope of, the slope coefficient. Okay. And this is our y-intercept. Okay. So we set the y-intercept to be 0. All right. Now, if we want more data, and typically we do in this class, we're going to set this to true. And so this is going to be the standard error of the slope coefficient. Efficient. It's the Shannon. Oh my gosh, Shannon. All right. All right. So these other numbers actually mean something too. But for us, we're just going to stick with this. So the slope coefficient is the spring constant. Okay. And so since the spring constant is the slope coefficient, then the standard error of the slope coefficient is the standard error of the spring constant. Voila. And what I want to do, I like to do this a lot. I'm just going to go ahead and say copy this, and I'll just place this function right in here, paste it, hit return. I'm going to go ahead and take both of these, okay, and I want to merge and center them. So when I merge and center them, you can see that you can get a lot more information here. And I typically try to merge and center to the point where you can see the entire function as opposed to it being cut off. So I don't have to hover over this so that you guys can do the same thing while we're having our conversation here. All right. So we basically, this is what we were looking for. Okay. And when it comes to the uncertainty, you also need this. So I'll make this color like green. And so let me go ahead and say that this is the uncertainty that you would find on Pasco. Okay. The standard error. Typically it's the first standard deviation, but we don't have the standard deviation here. All right. So let's see if we can produce ourselves a chart. Okay. First thing that I want to do, I'm going to go ahead and insert this, and I am going to say equals to. There's a better way to do this. And if you guys figure it out, hey, thank you. Please inform me. So what I want to do, go ahead and increase my decimal place 1. What I want to do is I want to chart the wire twist angle in degrees versus the gravitational force acting on the sphere to be charged in newtons. So the first column will be on the horizontal axis. The second column will be on the vertical axis. So let me go ahead and insert, go to the insert tab, and then I want to go to scatter plot, and I am going to use the scatter plot. Don't use the line. That line is superfluous. Don't use this line or these or this. Please, no bubbles. None of the, that's pretty. Okay. But no, use this. Okay. And so let me just move this down a little bit so we won't cover up our data. And also let me decrease the size of the focus. All right. So the first thing that you want to do when it comes to a chart, labels, axis labels, please just get it out of the way. Just don't wait. So we know what's going to be on the x-axis because we define it. It is the wire twist angle, and this is going to be in degrees. So we apply our appropriate formal specificity. And then in this particular case, we're going to have the gravitational force, and this is going to be in newtons. So you can see this is the gravitational force acting on the sphere to be charged, and this is correlated the wire twist angle. Okay. I think that's very descriptive as to what you're talking about. Okay. And so what we want to do now is we want to add a trend line. Okay. So I want to double click on this trend line. When I pick this, I can always go here and say more options, but I find it to be a little bit easier just to click on the line. I think I can double click or click, but and then select trend line options. Okay, so you see that it's already on linear. What we want to do is we want to display the equation on the chart. We want to display, and I'll go ahead and set the y-intercept to 0. Okay, and then I want to display the r-squared value. The r-squared value tells you how well the actual line is fitting, or it's getting close to the centers of these points. So it's the closer to 1, the better. Okay, so what I want to do, we can't tell what's happening because we don't have decimal places here. So let's go ahead and change this to scientific. It's already in scientific. And since we have 1, 2, 3, 4, 5 decimal places here, we don't have to have that many, but let's put 5 here so that we can see that we're getting the same value. So Linus will give you the same value as this particular technique, but you get a chance to see the model. So you want to visualize, you want art. Okay, this is like art. All right, you want a picture, and you also want the math to connect to the picture. You're gonna, because once you go to a high level of language, you speak in pictures, and so and not just, oh, your technical prowess. I think that's great that you can do that, but even in that, you want it to relate to a picture. Now, if I pick this line again, and I just want to show you something. If I take off the y-intercept, watch what happens to this number, this slope. The slope changes to 1.37. Now we can just go ahead and round it up if we want to and say it's 1.4. 1.37, 1.44. So how are we going to really say which one do we use? Do we set the y-intercept to 0, even though we have data showing that the y-intercept is not set to 0 when we take it? Which one is better? And then if we look at the let's see, the r-squared value, does it change? How well does it change? Set it back. So right now it's 9.98. If I set it here, it's still 9.98. Okay. All right. So that's the meaning of all of this. Cool beans. And that will be the end of this video.